So today we will first we will first see the results related to a Matlab program applicable for a cantilever beam and as well as for a fixed beam. So the Matlab software program, it has been used to produce natural frequency as well as mode shapes for the beams. The same program can be easily used, modified to find out the dynamic responses for a simply spotted beam also. Okay, this is the basic interface for a MATLAB. Uh, for most of my students, you might be learning this software for the first time. Over here, you can see this is the command window. Here, you will see the output of the MATLAB. Whether any matrix value, for example, over here at present, I had already checked the program. So first 5 natural frequencies in hertz, it is showing the output of the finite element model for a spectral beam. Over here, this is the workspace. This is workspace. Here you can see different variables are shown over here and their corresponding values are also shown. For example, in my program I defined a beam, area of the beam, and its corresponding value in SI units is this. Then C is the damping matrix. So for a very simplified example, the damping matrix size is 60 by 60, so it is showing that 60 by 60. This is the size of the matrix. If it is a scalar, it will show its value, and if it is a matrix, it will show its size. For example, modulus of elasticity of beam, here it is showing its value in SI units, and frequency in hertz, so here it is showing its size because that is gonna be a vector. And I calculated 30 frequencies, and out of these 30, the first 5 natural frequencies are shown over here. And to create a new file, you simply click over here as in any other software. To open an existing file, click over here, and to save or save as, you click over here file, and then simply in any other software you either click on save or save as and select the folder where you want to save. Okay, this is a normal MATLAB file, MATLAB program. So here a sample Matlab program is given here. Let me clear the annotation. So now you can see the output. This is a finite element beam model, and the output is natural frequency and its mode shapes I have shown here. You can also easily plot the FRFs also. So in this class I'll be showing the natural frequencies and mode shapes. So here I am just pressing F5 now. So once I press F5, it helps me in running this program. So F5 function button will run the program, and this is the output of the program. First 5 natural frequencies of the beam, and this is the first mode shape, and its different uh, configurations are also shown. Like this is the extreme condition. When the beam will vibrate, the extreme geometric configuration will be between this curve and this curve, and the intermediate configurations are also drawn in this diagram. This is for first mode. However, if you want to make use of however, if you want to see the other mode shapes, we can do that also very easily. So only thing is I will have to make a little modification in the program. So here this is the variable mode to be printed, which mode you want to print. So at present I had selected it to be 1. Let us make it 2. Now again I press F5, and then you can see this is the second mode shape. for a cantilever beam. This is applicable, this Matlab program is applicable for a cantilever beam. This is the second mode shape, and again here you can see this is the extreme condition, extreme geometric configuration. So it is like this, and the opposite also, opposite to this one is the other extreme condition will be this. So in second mode you will see there is one point over here where there is no displacement at all. So this we have just seen it theoretically through the finite element method. Even if you perform some sort of experiments, that if you take a cantilever beam, so I am first drawing a cantilever beam in blue color. Let's say this is the cantilever beam, and there I excite this beam using an external exciter, let's say vibration shaker, using a sinusoidal signal with a frequency same as second natural frequency, let's say that is 31 Hertz, right? So if I excite this beam at 31.1 Hertz exactly, then its mode shape would be, experimental mode shape would also be like that. And if you place over here above this, if you place sand above on this beam, let's say sand particles are placed over this beam, then when this beam will actually vibrate, so what will happen, the sand particles which are away from this point, this particular point where there is no displacement, so sand particles will fall down from these locations, and there will be only one location, this one, where the sand particles will be present. So that is how experimentally also you can find out the, you can say, such kind of points where there is no displacement during vibration. This is the second mode shape, again obtained through finite element only. And if you want to see the further mode shapes, let's say mode shape number 3. So here you can see the output third mode shape. So now there are two nodal points, right? So one is over here, one is over here, and another is over here. So how to experimentally verify this? The procedure will remain the same. Apply sand over the surface of the beam and excite it at a particular natural frequency. In this case, the natural frequency would be the third natural frequency of this beam, and here it is 87 Hertz. So it will depend on which frequency you are exciting the beam. If you excite at 4.9 Hertz, then you will not see any such nodal points. There will be only one nodal point near the cantilever beam fixed end. And for second mode shape, you will excite at this frequency. For third mode shape, excite at this frequency, and so on. Otherwise, if you excite the beam using an impulse hammer, so then a combination of different modes get simultaneously excited. There also the beam will be vibrating, but not at a specific particular mode of vibration. There many modes of vibration will simultaneously get excited, and the actual combined mode shape will be a combination of the different mode shapes of the beam. Now let us change the boundary conditions here. So for changing the boundary condition, we go to a different function which is being used in this program. So what I do here, to make it a fixed beam, I change the boundary condition by doing some control T, by applying control T. By earlier, at present, earlier this was like this, like percent sign was here. That means this statement was not getting executed. Percent means you can see the statement is now in green color. So this will not be actually considered as a statement to be executed. So I simply select this and press Ctrl T. Now this is in black color. So here these lines of the program will be actually executed. So how these are functioning, that we will see later. First let us see the output. Now after doing this, I will first save this program, save this function. So save this. Now return to the main program here, and here I will do a small modification, number of nodes to be 29. Now pressing F5. So this is the first mode shape for a fixed beam, where the two ends of the beam are fixed. So here I have to specifically reduce the number of nodes to be 29, because first node is also fixed and the last node also gets fixed. Now for second mode shape, I simply change the mode to be printed, that parameter value. So I press F5, and here you can see this is the second mode shape for a fixed beam. And for third mode shape, again pressing F5, this is a third mode shape, and so on. For a fourth mode shape, now pressing F5, this is a fourth mode shape, and here you can see the curves are not very smooth over here. Here you can see within this portion the curves are not appearing to be very smooth, right? These are appearing to be a combination of straight lines. Now this problem can be reduced by increasing the number of elements. So here if I increase the number of elements, let's say to 100, and number of nodes here to 99. Now let us see what happens. Okay, here the x-axis is not coming properly. Let me press F5 now. Actually the x-axis has been limited to show the variation between 0 to 30, I think. So that setting needs to be corrected. Here I am now converting this line of the program into a comment by pressing Ctrl R. So here you can see the x limited value is decided in this particular line of the program. Now let's press F5. So now you can see the effect of increasing the number of elements. Earlier when I was using 30 number of elements, then the mode shapes were not so smooth in the mode shape diagram. But when I increase the number of elements to 100, now I am getting a clear cut mode shapes. A very smooth mode shape is appearing. Same is the case with the cantilever beam also, or any other beam, or any other model also. So one may suggest that why not you increase the number of modes to 100 every time, but because that will give a better picture of the mode shape diagram, right? But the problem is when you increase the number of elements in any program, its computational requirements also increase a lot. And here this is a very simplified program. Here we are having a very simple finite element program for a very simple application, a beam. But in real life, the actual finite element models can involve millions and trillions of elements or nodes or degrees of freedom also. So there we need to define the node in a very optimistic way, so that you get a clear picture also, and at the same time the computational time should not be very long. Sometimes the computational time may exceed 1 day, it may also exceed 1 week, depending upon the complexity of the finite element program. So now let us reduce the number of elements to only 10, and here I reduce the number of nodes to be 9. Now I am pressing F5. Now see the mode shape diagram which I am getting, right? So that is the effect of selecting appropriate number of elements. So here I am selecting again, coming back to the original values 30 and 29. Now pressing F5. So this is the output. For node number 0 and this end of the beam is fixed, so ultimately it should converge to 0, and on this side also all the curves should be converging to 0 for a fixed beam. So I hope I have been able to induce some interest into this topic to all the students. So you can see how interesting is it to draw such plots using Matlab, and it is really very easy to use this software. Now we will have a quick introduction about the basic commands of the software. So here is a very quick introduction about Matlab. It is basically the matrix laboratory. So here Matlab is matrix laboratory. It was developed by a Professor Clay Moller at University of New Mexico. This person, you can say, you can see here, he is Professor Clay Moller, and the other one is, I think he was from Stanford University, engineer Jack Little. So these two persons are the main founder, right? And Professor Moller is, I think he was a mathematician earlier. So the purpose of Matlab when they developed it was basically numerical computing. Then later on symbolic computing was also included, and Simulink is also there. Some other aspects, its value was $1 billion MathWorks in 2018, and ever since 1984 it has been profitable every year. Not even a single year where this company reported any kind of loss. It was profitable every year. This software Matlab is used in 185 countries. There are more than 4 million users across the world, and 2000 books are available related to learning of this language, learning of this Matlab programming language, and 27 languages are available. In 27 different languages like English, French, many other languages, the books are available. And it is used in a wide variety of applications, not just in finite element. It is used by used in thermal analysis also. It can be used for commercial analysis. It is very much used by commerce people also, and many other applications it can be used. So here you can see this is a basic introduction to Matlab. Command window we have discussed, workspace we have discussed, current folder. Current folder is the present folder where you are working, right? And command history, it tells you about the previous commands which you have used. And a equal to 2. So this is how we define a variable in Matlab. We can create a new file here. So by clicking here, I create a new file. So in the Matlab command window, this is the Matlab command window. You can see output of some previous program, right? So I do not want to see this output of the previous program. So what I do, I go to my Matlab program, and at the start of every program, I first write CLC. CLC is for clearing the screen. Now I press F5. So it will first ask me, where do you want to save? So I say 2021. Okay, this name will not work properly, I think. Your Matlab file name must start with an alphabet. So I say introduction. Space should not be there. No space allowed in the file name for Matlab files, Matlab program files. So underscore you can use. So introduction underscore 2021 underscore 05 underscore 12. Save. Now it has saved also, and it has run the program also. See the effect of running the program over here. The command window has been cleared. This command window is clear now. But here still in the workspace you can see, in the workspace the previous programs variables are appearing in the workspace. So I want to clear this workspace also. So how to do that? I add one more line into my program, clear all, and then I at the end of every line I add a semicolon here. So we'll see later what is the effect of this semicolon. So clear all. Now again I am pressing F5. So here as soon as I press F5 you can see the workspace has been cleared, right? So here you can see this command window is like a whiteboard which can be cleared using CLC command, and this workspace is like a brain where if you want to delete the previous memories of the brain you can do by just executing one command, clear all. See how easy it is to clear previous memories of the brain in a computer. How easy, by just running a statement, clear all. And for us, for humans, how difficult sometimes it becomes to clear the previous memories. And if you want to clear the figure as well, CLF can be used. CLF will clear all the previous figures. Any previous figure is run, that can be cleared using CLF. Again pressing F5. So here you can see figure 1 has been cleared now. Now you can draw on this figure. So I am now coming back to the my presentation. So here a is equal to 2. So now let's see what happens. I write a equal to 2 and then I press F5. So now see its output. Its output will be over here. Here you can see it is showing the output a equal to 2, right? It is showing that there is a variable a defined in the memory of the computer workspace. In the workspace you can see a is shown over here now, and its corresponding value, because it is a scalar, so its value is also shown over here. But once if it is being shown over here, then there is no need to repeat the same thing at the whiteboard also, in the command window also, right? So to avoid this repetition every time for all the variables, so what I do, instead of writing a equal to 2, I say a equal to 2, then I insert one extra thing, that is a semicolon. Now I press F5. Now I see the command window. What will happen? CLC will be executed. That means command window will be cleared. The whiteboard will be wiped off. Clear all will be executed. Workspace will be cleared. The brain of the computer will be cleared. Then CLF figure will be cleared. A equal to 2, a variable will be defined, a equal to 2. But it will not be shown on the command window. It will only be defined and computer will store it in its workspace. So this is the output you can see here. Here a is equal to 2, that is defined. Here you can see a is equal to 2 is defined in the workspace, but in the command window nothing is shown. So that is the advantage of using a semicolon at the end of each and every statement of Matlab program. This not only helps you in keeping your command window neat and clean, it also helps in reducing the computational requirements also, because if the software is writing something, it will definitely take some amount of time, some fractions of seconds will be taken in writing or displaying the variable values in the command window. Now we define another variable b equal to 5. Okay, let's go to the program. So here I define another variable b equal to 5. So here I write b equal to 5. Again a semicolon, I add a semicolon here. Now I press enter, then I press F5. Now I see the effect in this Matlab window. So a equal to 2 is defined, then b equal to 5 is also defined. So next there are some common operators like plus, minus, multiply, divide, then raise to the power and then square. So these are the common variable. This is divide and this is raised to the power raised to the power, and then sqrt is square. So this is I think it is self-explained. So you can say C is equal to A plus B, right? So that C should be 7. Now press F5. See the output. So here the output is shown, C is 7. Now again minus, let's say D is equal to A minus B semicolon, press F5. So here you can see D equal to minus 3, E equal to A divided by B semicolon, press F5. So E is calculated and stored in the workspace also. E is 0.4. Okay, then F equal to A raised to the power B. Now press F5. So here you can see F is A raised to the power B, that is 2 raised to the power 5. So that is 32. And G equal to sqrt of A semicolon, press F5. So G is 1.414 to square root of 2. Plus minus multiply divide, plus minus multiply divide, multiply is missing, so we can do that. Let's say H equal to A into B. In this multiply sign is actually star, multiply sign. So semicolon, press F5 and see the output H equal to 10. 2 into 5 is 10. So these are the basic mathematical operations. Then WHOS. So let us see what happens with this command WHOS. So I apply this command here, WHOS. You can directly see the effect by writing this command in the command window, then you press enter. So this will tell you all the variables present in the workspace, their size, bytes, class, attributes. All the details will be shown. Okay, next we are having CLC for clearing the command window. CLF is for clearing the figure window, and clear A. If you want to clear a specific variable, then you can write it this way. If you want to clear more than one variable, you can write it this way. But generally what I do in the very start of the program, you might have noted earlier, in the very start of the program I always write clear all. So that will clear all the previous variables. So I generally prefer to use clear all, but sometimes some requirement is there, so you can clear individual variables also one by one by using this format. Okay, then there is a very important command help, right? So for that, for example, suppose you do not know the plotting function, right? How to plot? So simply write help spacebar then plot. This is the basic command which is used for plotting in Matlab. Now press enter. It will tell you most of the details and very helpful for most of the for all the commands. This command help can be obtained using this method. Just type help, press spacebar, and then type the type the command name, and it will tell you plot. It will give you a linear plot, and then the format of the command is explained. It will plot vector y versus vector x, vector y on y axis and then x on x axis, and then it will give you detailed description also. If x or y is a matrix, then the vector is plotted versus the rows or columns. So all the details you can see here. Even by taking help, you can learn so much regarding Matlab, and mostly it also tells you some examples also. So what you can do, you can simply copy the example from here and then paste it into your sample program. Paste it over here Now let us press F5 and see the effect. So this is the output of the program now by using the code which I simply took from the help command, by using the help command. So this is a sample plot. So step by step you can understand by copying and pasting the codes which you get from the command window by using help command. Okay, a better version for help, getting the help is look for, because sometimes you do not remember the exact command name also. So there you can use look for command. So in look for you can see here, if I type look for then space bar and then plot. Now press enter. So it will give me all the details of all the commands in Matlab which are related to plot. And then from here I can find out in which command am I actually interested, whether I want to take a help on plot for plotting linear plot, or I can also go for gplot where for plotting graph as in graph theory, or I can look for tree plot. There are so many commands which involve the word plot, right? So ODE plot can also be done, right? Time series ODE output function. So there are so many commands. It will list you all the commands. It will give you an option which command you want to use. So plot 3 is used to print 3D, print in 3D space. Okay, so you can use look for command also if you do not remember the exact name of the command which you are looking for.